signals that show up in that roughly that region.
Double bonds?
Carboxylic. Alkanes. Hydrogens? No, what's that? One.
How about aromatics?
Yeah.
Carboxylic.
7. Yeah. But you don't have any carboxylic stuff in your compound.
Okay.
But you do have some aromatic from the pyridine, right?
Okay.
All right. So remember, NMR is all about symmetry.
Mm-hmm.
So how many different kinds of hydrogens do we have?
2.
Try again.
3.
3.
Yeah.
So if you cut it in half, this one, these two, and then these two.
Yeah.
Right? And then, so if I want to know, if I'm looking at this signal, how would I know what it should look like? Is it going to look like a singlet, a doublet, a triplet? How would I know?
It's going to be a triplet. What is it?
Triplet or single?
See, it's complex.
In this case, it's not going to be complex. So what is our general rule? N plus 1. How many hydrogens is it next to? Just this one.
Yeah.
So this one should look like a doublet. Okay. What's this one going to look like? A triplet. What's this one going to look like? A triplet. So how am I going to tell these two triplets apart?
Closer to oxygen. Closer to the
The nitrogen.
Oh, nitrogen.
How far down it is?
Okay. Yes, you learned that nice rule in organic, but it's a general rule. It's not a golden rule. The only golden rule in organic chemistry is that there are no golden rules. Okay? Normally, what you would say is, yes, as we get closer to the nitrogen, that should push it further downfield, right? Well, this nitrogen is actually connected to a metal, so that kind of throws things off a little bit. Okay? Now, how could you tell the difference? Well, we tell the difference by integration, right? The signal is only going to do to one hydrogen atom. You're going to see a triplet that only has one, that's only made up with one hydrogen. This one is going to have 2 hydrogens, so it should have a bigger integration. That triplet should be a bigger triplet, right? So let's zoom in here. So here's our doublet. So this one here is, of course, the one next to the nitrogen.
Yeah.
But you notice we have a triplet here and a triplet here. This is this, and this. Your stuff's falling apart a little bit. You can't help it. Okay? In organic, you get the nice, pretty spectra. They're all nice and clean. There's no impurities. Well, that's not the real world. This is the real world. Okay? So we have 2 triplets here. Which one is probably going to have a bigger integration?
Right.
This one. So this one is going to be the meta hydrogens to the nitrogen. And then this one is going to be para. Okay?
So triplet, doublet, triplet, coming all the way down.
Triplet, triplet, doublet.
Oh, whoops.
And I'm going to, for every group, I'm going to print this off, and I'm going to give you guys multiple copies. So I'll have one where it's going to be like the whole spectrum, and then I'm going to zoom in like I did here, all these
So
regions.
the middle one would have a large signal.
This one?
The one at the very top has a large signal.
No. It's a smaller. It's a smaller
That's
triplet.
the
So
doublet.
the one that's
Or
meta
the
is-
triplet right there, yeah.
Huh?
The meta?
Yeah, the meta one's going to be the bigger one.
Yeah.
All right. So that's the aromatic region. So that takes care of the pyridine, and so this is the whole shebang. All right. Now we come down. So this stuff, all this stuff here is garbage. Okay, and now we're going to come to this little region in here. Little. Yeah, this could have been shimmed a little better, but it'll work. I don't care how your spectrum looks. It's just that you have the spectrum. All right, so we have this ginormous peak. So if we looked at the whole thing, this is the biggest peak in the whole spectrum. What thing would contribute the most hydrogens to that signal?
The methyls.
All the methyls, right? Because it's symmetric down this way. So I've got 3, 6, 9, 12 hydrogens, right? Okay. So the tallest peak is going to be your methyls. Okay. Now, we also have this little weird-looking thing right here. It's supposed to be a quintet. Doesn't look like a quintet because the shimming is off a little bit. But it is a quintet if you look in the structure, there is nothing that's next to 4 hydrogens to give a quintet. But what do you have in your NMR tube besides your sample?
Water.
Solvent. Your solvent is acetonitrile. Acetonitrile, it turns out, nitrogen is a spin 1 nucleus, and so what that means is you don't have a nice singlet that you would expect to see from the 3 hydrogens on these solvents. It's actually a quintet. So this is your solvent. Okay? This peak right here, whenever you see something that's nice and broad, that is a good suggestion that it's probably some sort of a protic solvent. And what sort of protic solvent might you have used in the synthesis and or recrystallization of your compound? Water. Not water. Methanol. Okay. So this would be the OH in the methanol.
Okay.
Okay. It's kind of broad. All right. Now this one is junk. Then we have this signal right here. This signal is not obvious, but it turns out that it's remember the dimethylglycine has 2 acidic hydrogens. Only one of them comes off when it binds. And so we have 1, 1. So this signal at 2.7 is for the dimethylglyoxines, hydrogens. Okay. And if we had done this in, say, deuterated methanol, we wouldn't see those signals because the OD in the methanol, the D would exchange with the H's here. And then because the solvent's in huge excess, now all these are D's and you don't see anything because we're looking for protons, not deuterons, or protiums, not deuteriums, okay? All right, now, it's not super obvious again, but we also have this funky looking thing right here. Now, it's not a great signal, but take my word for it, it is actually a septet, or a heptet, however you prefer Greek or Latin. What in here would give rise to a heptet or a septet?
The methyl.
Metal.
That hydrogen right here in the middle, right? Because it's next to 2 CH3 groups. So you'd expect to see 7 peaks. You don't see them because there's only how many hydrogens? 1. So you don't. It's not big, but that is that. And these little things here are again garbage. Okay. So we have now identified all but one set of hydrogens. The only thing we have left are the methyl groups here. What should they look like?
Well, split by doublet.
They should be a doublet. Dun dun dun. There's your doublet. About 0.9-ish. These are all not being referenced exactly the same, so some people's may be slightly different numbers in terms of their chemical shifts. Some people use the acetonitrile that had TMS in it. Some people didn't. This does not have TMS in it. If this had TMS in it, we would see a signal right around 0. That's tetramethylsilane. That's this internal reference. So, for example, so there would be this would show up, but not all the ampules had TMS in it, so not everybody's going to have that TMS peak. And the NMR is smart enough that you can say, hey, I want you to reference the peaks according to the solvent or by TMS. So it did it by solvent. Well, acetonitrile is not actually a bad ligand. It can actually coordinate to the cobalt as well. And so that may be some of the reason why things are falling apart a little bit, is that maybe displacing the pyridine or something.
Okay.
All right. So if you look at other people's and they have something around 0, that means they had TMS in their solvent, which is fine. You didn't. Okay? And what I'm going to do when I get back is somebody can have, I'll print off a copy, somebody can have that copy. But what I will do is I'll print off a full spectrum and then I will zoom in to each region like we just did, and I'll send you those as well.
Okay.
And then you can submit what you want to submit.
Okay.
Sweet. Did you get ours out of there?
No. Let me give you
Send me that video.
Yeah.